Okay, so I'm just going to work through the answers for the third weekly test. On the whole, the class is now really spreading into two camps. We've got those who are doing very well; they know their work at this stage, and we're getting good marks. And those who are struggling. Within this question paper, that there were a number of you that were making very small mistakes. Typical types of mistakes, and most of those could be avoided if you just count your carbons. Make sure that you're not losing out on any carbons. Okay, so this is the enamine solution to the aldehyde problem. So we form the enamine, we're then going to alkylate at this position over here, and then we hydrolyze the iminium or enamine that's remaining to get back to the aldehyde. So the product basically looks the same as we've got the aldehyde there, and we alkylate at this position, and we put on the allyl group, which is 3 carbons. Okay, and that's where a lot of you made a mistake, was by not doing that. All right, the next question is 1,3-dicarbonyl, and we see that here we're going to do, at the end of the alkylation step, we're going to be hydrolyzing and then decarboxylating that. There's our electrophile. So we generate with sodium methoxide, we're generating at this position here, negative, going to come in over there, kick out, and then that's going to get hydrolyzed, and one of those is going to be removed. So the product will look like this, NO2, and then there's the carbon there, and then that's the new OH. All right, so this is the bond that was formed, and this carbon is where we decarboxylated from initially. That would have been 2 marks for that. This one over here, the key thing here is that we're using sodium hydride refluxing, so we're heating up and taking some time to that. So we're going to form the thermodynamic enolate, which is on this side here, not that side there, on this side, and then we're just adding an electrophile, which is not terribly exciting. And so this was relatively well answered. So we get the phenyl, and we're forming the new one over here. It's 1, 2, 3, 4 carbons, and the fifth one's 1, 2, 3, 4, and there's the, okay, easy. Then this question over here was surprisingly answered quite badly, and I think I know why. It's because instead of writing TMS chloride, I actually wrote out the trimethyl silyl chloride. Okay, it's the same thing. I just did it slightly differently. But if you got it, you realized that the TMS silyl enol ether, TMS, is going to be the thermodynamic one, and it's going to form like that over there. In order to get the TMS group off, in order to get the enolate like this, we need to add methyl lithium. Not many people got that correct. There's only about, I guess, 3 of you or so in the class that got that, but we had covered that in one of the lectures, and also it's in your textbook, and we did it in the class. And then lastly, this one over here, a recognition that the bond that we formed is that one there, and so our electrophile is going to look like this. There's going to be, it needs to be a plus here. All right, so the easiest way to do that is put a leaving group on. The easiest leaving group we can put on is the bromine. A number of you ended up putting an extra carbon here, which was incorrect. But the important thing here is that if we want this to react with that, we need to react at this position over there. And so now we've got 2 options next to the ketone, which an enolate can form. If we want to form it over here, we need to do it via the kinetic enolate formation, and the solution to that is using LDA at, of course, minus 78 degrees Celsius in THF. And we have to form that first step, and in the second step we're going to be adding the electrophile, and that will give our correct product. There we go, answers in under 5 minutes, and that's pretty much what you should be able to do.